Thank you for joining this lecture series. We'll give the lecture series on machine learning, and today's topic is eigenvalue, eigenvector, principal component analysis, and linear discriminant analysis. And we'll also talk about an application. So basically, this series of lectures consists of 4 lectures. The section 1 is about determining eigenvectors and eigenvalues of a square matrix, and then eigen decomposition of the matrix. Section 2 is about how to calculate what is covariance matrix and what is scatter matrix. And we'll also see how what are the eigenpairs and how they're related to principal components of a data. Section 3 will give some application of principal component analysis. 2 main applications will be dimensionality reduction and data visualization. And we'll also talk about an application which was proposed in MIT in 1991. This is about face recognition, and it's famous with the name eigenface. And the last part will be linear discriminant analysis. The overall picture here is about dimensionality reduction techniques. Okay, so if you see the dimensionality reduction technique, there are 2 types of approaches. One is linear method, and one is nonlinear method, or you can say manifold learning. So basically, in this section, we'll be in this section of linear methods, and we'll talk about principal component analysis and linear discriminant analysis. We'll not talk about metric multidimensional scaling. This will be taught in a different lecture. Now, the first and very basic thing is how to find the eigenvalues and eigenvectors of the matrix. Okay, and this part consists of 6 slides. So first of all, what is the definition of eigenvector? If we have of course, eigenvector and eigenvalue is what we discuss here is related with square matrices, and of course for rectangular matrix also we have pseudo or inverse, and those things we'll not discuss in this series. So if we have a square matrix M, then eigenvector is defined as M into V equal to lambda V, where lambda is a scalar constant. Okay, if you look at this equation looks like a matrix is converted to a scalar lambda. So in that way, the eigenvalue lambda in a way represents the value of the matrix in scalar. Okay, so we express the norm of a matrix in terms of its eigenvalues. Okay, and V is the eigenvector, and let us see how we can find the eigenvalue and eigenvector of the matrix. Okay, and as I just mentioned, M is a square matrix of dimension D into D, and so if this equation is valid, then we can also write M minus, bringing the right hand side to the left hand side, we can write this. And when eigenvector is non-zero, then we can write that determinant of M minus lambda equal to 0. So this is a polynomial equation. And the solution, because we know M and I also we know, so it from the polynomial equation, we can find the value of the lambda, that is eigenvalues. Okay, we give it we explain with a small example. For example, our matrix is this matrix 3, 2, 2, 6, and then using this equation, determinant of M minus lambda equal to 0, we can write this equation, determinant of our matrix M minus lambda into I is lambda 0, 0, lambda, and it converts into a polynomial equation. Because the matrix is of dimension 2, our polynomial equation is also of dimension 2. Now solving this equation, we have two values of lambda. One value is 2 and one value is 7. Putting those values in the original equation, we can find the eigenvectors. Okay. So the matrix, the eigenvector we don't know now, so x1, x2, and eigenvalue 7. Now solving this, we can find the value of eigenvector as 1, 2. And when the eigenvalue is 2, we can find the corresponding eigenvector as minus 2, 1. Please note here that V1 and V2 are, orthogonal vectors. That means the dot product is 0. Okay, it always is like that. They are perpendicular to each other. And if we put back in the original equation, you can see that the matrix into the eigenvector is equal to eigenvalue into the eigenvector. You can verify very easily. Okay. But actually, if 1, 2 is an eigenvector, you can easily see that 2, 4 or any scalar multiplication of 1, 2 will also be an eigenvector. So what will, it's not a standard. Eigenvector is not a standard if you write by 1, 2. Okay. So usually to standardize that, we normalize it. Okay. So we normalize a vector 1, 2, and because the norm is root over 5, 1 square plus 2 square and root. So we divide by 1 by root 5 and 2 by root 5. And this is a normalized vector. The normalized vector means its length is 1. Okay. So after normalization, we have the two eigenvectors as this and this. The problem in solving the eigenvalues and eigenvectors, actually first we find the eigenvalues, then the eigenvectors. And the problem with this approach is that if the dimension of the square matrix is very high, say 100 by 100, and it happens, in many practical cases, it could be even larger. In that case, a polynomial equation of the very high degree is very difficult to solve. And not only that, in many applications, we need only the first few eigenpairs. By telling first few, I mean the first few eigenpairs where the eigenvalues are in descending order. So the highest eigenvalue, the second highest, the third highest. In that way, if we can calculate, then we really don't need, in applications, we really don't need to calculate all the eigenvalues and eigenvectors or eigenpairs. Basically, if it is a 100 by 100 matrix, we have 100 eigenvalues and 100 eigenvectors, but the first 5 or 10 is sufficient for most of the analysis. So here is another way to find the eigenvalues, and in a descending order. In this way, we can find the largest eigenvalue first, then the second one, then the third one, like that. Okay. And the method is very simple. It's an iterative method, a numerical iterative method. And this is the equation we use. So k is the number of iteration, and this xk is our eigenvector. So in this approach, we first find the eigenvector and then we go for the eigenvalue. It's the opposite of what we have seen last. So by iterative method, I mean we start with a eigenvector with some approximate value or some initial value, and then we iterate this equation, and slowly after 3-4 iteration, we can, the value does not change. That means it converges, and that is the eigenvector. And here again, we will show with a small example. Actually, we'll use the same matrix as the last time. Okay. So the initial value of the eigenvector, usually we start with 1, 1, 1, 1 like that, and then we iterate. And please note that when we do like this, the eigenvector is actually normalized. We have to use the normalized value of eigenvector when we do the iteration. But for the first time, the initial value, it's not normalized. Okay. So I've mentioned that k for all k greater than 1, greater than or equal to 1 is normalized. Let us see how it is done. So we start with the same matrix, and let us consider that the first eigen vector is 1, 1. Okay. by first I mean it corresponds to the highest eigenvalue. Okay. So using the previous equation, then after the first iteration, the x1 will be like this: the matrix into the initial value of the eigenvector divided by the norm of the matrix. Okay, so if you do, it is getting normalized, and then we have this value. So this is the first iteration. First iteration value is 0.53, 0.84. And the second iteration, you put the value from the first iteration, you do it again. And you can try that within 4 iterations, it value converges. Converges means further iteration, the value does not change much. And this value is same as the value we received by using characteristic equation, by using the first method. Okay. So this is the first eigenvector. Now, once we get the eigenvector, we can find the eigenvalue using this equation. So this is the eigenvector. You take the transpose, multiply the matrix, and you get the eigenvector. So if you do that, you get the eigenvalue. It's very easy to prove that it will give the eigenvalue because we started with the eigenvector transpose mx, but mx is actually eigenvalue multiplied by the eigenvector. And because it's a constant, you can take it in the front, and xt into x is 1 because they are orthonormal vectors. Okay. So in that way, for the eigenvector 0.447, 0.894, we find the eigenvalue, which is actually, it's a little approximation. So we get the eigenvalue of 6.993, which is very near to the actual value 7. Now, what about the second, third, fourth eigenvalue and eigenvector? Okay. So the method is very simple. From the original matrix, we subtract this. The first eigenvalue, then first eigenvector into the transpose of this. Of course, the eigenvector into its eigentranspose will give a d by d matrix. So we subtract that matrix multiplied by lambda 1 from the original matrix, and we get M1. Now, we again use the same method of iteratively finding the eigenvector. So if you run the same method on M1, we start with again a eigenvector of 1, 1 and do the same. Then we get the second eigenvector. From second eigenvector, we get the second eigenvalue, and we repeat this process. Okay. The proof is very simple. I'm not going through that. I just want to mention that the matrix can be expressed as the sum of the eigenvalues into eigenvector transpose. At the end of this lecture, I'll prove this. Now, if from this matrix you subtract the first one, lambda 1, B1, B1 transpose, then what is remaining is from lambda 2 to the rest. Okay. So lambda 1 now becomes 0. So if we find the next eigenvector, the highest one will be lambda 2. So in that way, we can go on finding next. But as I told you earlier, we really don't, in most of the applications, we really don't need to calculate all the eigenvalues and eigenvectors. And in most of the applications, even the original matrix M is 100 by 100 or 1000 by 1000. We'll show with an example that the first 7, 8, or 10 eigenvalues and eigenpairs, eigenvalues and eigenvectors are sufficient for any analysis. Okay. And we'll conclude this section with a few important things to remember, some important definitions, I should say, or some important relations which we'll use in subsequent section of this lecture series. And the first one is just a definition. So the definition of Hermitian matrix. Hermitian matrix is nothing but symmetric, but when the matrix elements are imaginary. So if the matrix elements are imaginary, then Hermitian matrix is the conjugate transpose of the same. If we take the conjugate transpose and the original matrix, they are the same. That is Hermitian matrix. And if the elements are real, then we call it a transpose, just transpose. And so it's actually symmetric matrix when the elements are imaginary. We call Hermitian matrix. Please remember, the following are some relations. They are important, and they are important in many respects. And I will use these relations in subsequent section of this lecture. So please remember them. So first of all, the trace of a matrix is the sum of all its eigenvalues, and the determinant of a matrix is the product of all the eigenvalues. And we actually already mentioned this, the spectral theorem, which is very important, has many applications, is that the matrix can be expressed in terms of the sum of all its eigenvalues into eigenvector and eigenvector transpose. Okay, and these can also be expressed like V. V is a matrix whose columns are the eigenvectors. Okay, and V transpose, of course, V transpose of V. And sigma is a matrix which is a diagonal matrix, and the diagonal terms are the eigenvalues. Okay, this and this is very easy to show that they are the same thing. Actually, we'll show it at the last slide. Okay, and using this spectral theorem, you can also see that it's easy to see that any function of the matrix A is actually function of the eigenvalue and the product of the eigenvector and its transpose. Okay. For example, if you want to raise a matrix to the power of k, we don't really do anything. We just raise the eigenvalues to the power of k. Okay. If we want to make the inverse of the matrix, we just make the inverse of the eigenvalue. So if the eigenvalue, first eigenvalue is 3, it will be 1/3. The second eigenvalue 2, it will be half, like that. Okay. And again, if you want to raise, a to exponential, then also we can write like the equation of exponential 1 plus 1 by x plus 1 by x squared. So we use the same equation to raise a to the exponential. And also the eigenvalues of a to the power k are the kth power of all the eigenvalues of a. And yeah, eigenvalues of A inverse are 1 by lambda 1, 1 by lambda 2, 1 by lambda 3. And if there are two matrices like A and K, where K is a scalar, then eigenvectors of the two matrices will be same, but the eigenvalues will be K times the eigenvalue of A. Eigenvalues of K will be K times the eigenvalues of A. With some numerical example, because it's easy to understand from numerical example. Let us see that those equations are valid. For example, we have a matrix A like this. Then it's easy to see that the eigenvectors, normalized eigenvectors, will be like this, and eigenvalues are, for eigenvalue 2 plus root 2, the eigenvector is 1 root 2 1. Like this, these three eigenpairs. Okay. So first of all, please check that for a symmetric matrix, all the eigenvalues are positive. Okay. All the eigenvalues are positive. It has another implication. We call this matrix is positive. Are non-zero and non-negative, 0 or positive, then that matrix is called positive semi-definite. Okay, so in this case, this is a positive definite matrix because all the eigenvalues are positive. You can also easily verify that the sum of the eigenvalues like lambda 1, lambda 2, lambda 3 is equal to the trace. The trace of this matrix is 2 plus 2 plus 2, 6, the same as the sum of the eigenvalues. The product of the eigenvalues, which is 4, is same as the determinant of the matrix. You can check that. And similarly, if we write this is the matrix consisting of all the eigenvectors. Eigenvectors are its columns. Okay. And this is the sigma matrix where it's a diagonal matrix and the diagonal elements are the eigenvalues. So if you do the product of this, you'll find we come back to the original matrix. Okay. It's also easy to verify the following equations, which you can try at home. And the last slide is the proof of this. Okay. So we mentioned that in the spectral theorem, we mentioned that a matrix A can be expressed like this. Okay. So it's easy to verify when you start from the right-hand side. The right-hand side is sum over all the eigenvalues into corresponding eigenvector and its transpose. But you see that lambda I vi is actually the matrix A into vi. So we write lambda I vi as A vi. Now vi and vt, if we multiply that, if we sum over all the eigenvectors, then this we can write as matrix phi, where matrix phi is actually matrix consisting of all the eigenvectors as its columns, okay, and the transpose of that, and that is proven here, okay. And so V, because phi consists of columns which are orthonormal, and Vt is its transpose. If we multiply, then we get the identity matrix. So into identity matrix is A. So we prove this. Okay. Similarly, we have to prove that A is equal to V sigma Vt, where V consists of, as I just mentioned, all the eigenvectors as columns. So if we write AV, so first column will be AV1, second column will be AV2, last column will be AVN. And because you know that AV1 is equal to lambda 1 V1, we can write this at lambda 1 V1 into lambda 2 V2, where V1, V2 are the eigenvectors. Okay. Now this can be written as V into sigma, where V is the matrix consisting of all the eigenvectors, and sigma is the diagonal matrix where the diagonal terms are the eigenvalues. Okay. So if AP equal to V sigma, then multiply both sides, or multiplying the right and both sides on the right multiplication with V transpose, we get A equal to V. V transpose is actually identity matrix. And then if we multiply this side with V transpose, it's V sigma Vt. Okay. So this is also proved. Please see that in this way we can decompose a matrix. Matrix decomposition is a very important way of extracting the inner information hidden in a matrix. And you had several ways of matrix decomposition, but probably this is the simplest way. This is also called a QQ decomposition of the matrix. Because why QQ? Because this V matrix in many cases it's expressed as Q. Okay, so it's also called QQ decomposition. And yeah, so this is one of the important matrix decomposition. We'll also go through singular value decomposition, non-negative matrix decomposition, all this in future. Okay, thank you very much. And let us join in the next section of the lecture.